Hey guys, so this is going to be part 2 of our lecture on section 4.1, finding absolute maximums and absolute minimums. Alright, so in this video, all we're going to do is be doing practice examples finding absolute maximums and absolute minimums. Yeah. Just a quick recap of that previous example. We were tasked with finding the absolute maximum and absolute minimum on the interval -1 to 2 of the function square root of 9 minus x squared. What did we do? We found the derivative. We set it equal to 0, solved for x. That gave us a critical point. We asked ourselves, when does this function not exist? We found those values that forced the derivative not to exist, and that gave us our critical points. But we didn't care about 3 and -3 because they were not in the interval -1 to 2. So we really just focused on these 3 points right here, -1, 0, and 2. And 0, that's where our critical point is. -1 and 2, well, that's the endpoints of our interval. But why do we only care about these 3 points? Because the extreme value theorem tells us that an absolute maximum or an absolute minimum of a continuous function on a closed interval only occurs at critical points or the endpoints. So rather than checking the entire interval for these absolute extrema, all we have to do is check these 3 points. How do we do that? Build a little table, take our values, plug them into F, and then from here we can determine that the absolute maximum is 3 and the absolute minimum is 2.236. I know I flew through that example, but that was the example we did at the end of the last video. Only reason I'm going over it again real quick is to kind of refresh your memory on what it is we're trying to do. We're trying to find absolute maximums and minimums. The extreme value theorem tells us we only need to check critical points and endpoints. So really the hard part is finding the critical points. That's it. So that's what we're going to spend the remainder of this video on. Practice examples. Why? Because the only way to get good at something in math is to practice. All right, that's enough of that example. So let's look at a new one. Let f of x equal x cubed minus 3x on the closed interval -2 to 2. Tasked with finding the absolute maximum and the absolute minimum. All right. Now, I would like to point out that this function is a polynomial. So its derivative exists everywhere. There is nowhere it vanishes. There's not going to be a division by 0, limits not lining up. Don't need to worry about that. This function is a polynomial, cubic polynomial to be more precise. So its derivative exists everywhere. When you take the derivative, it's still another polynomial. It's going to exist everywhere. So to find the critical points, we only have to determine where is the derivative equal to 0. Now, to determine where the derivative is equal to 0, we have to find the derivative first. Can't really ask it, where is it equal to 0, if you don't have it. It's like trying to ask somebody a question and them not being there. You can do it, but you're not going to get anywhere. So, we have our function x cubed minus 3x. We take the derivative, and we get the derivative equal to 3x squared minus 3. Now, we have to ask ourselves, where is this equal to 0? To do that, set 3x squared minus 3 equal to 0. Move that 3 over to the other side. Divide both sides by 3. And now we're asked to solve for is x squared equal to 1. But where is x squared equal to 1? At plus or minus 1. Take either plus or minus 1, plug it in there. X squared is going to be equal to 1, which means the derivative is going to be equal to 0 and x is equal to plus or minus 1. Excellent. Now, these are our critical points, and these are all of our critical points. Think about that. In one swing, we figured out where all the critical points were of this function. Not just on the interval, we figured out where they all are. Because critical points only occur where the derivative is equal to 0 or where the derivative does not exist. We already established the derivative is going to exist everywhere. And these are the only 2 places where the derivative is equal to 0. So these are our only 2 critical points. All right. So, since our critical points are x is equal to plus or minus 1, then we know from the extreme value theorem, we only need to check the critical points and the endpoints. And just remind ourselves, what are the endpoints? Well, We're only considering the interval -2 to 2, so our endpoints are -2 and 2. So the extreme value theorem tells us those are the only points we need to check. But of every number that is between -2 and 2, the only values we need to check are x is equal to plus or minus 1 and x is equal to plus or minus 2. Because that is the only places that the absolute maximums and the absolute minimums can occur. How do we check them? Build a table. So there is no order in which to check these numbers. You can start with +1, then -1, then +2, -2. It really doesn't matter as long as you get all of them. So I'm just going to go in increasing order. So for x is equal to -2, f is equal to -2. Wow, that was anticlimactic. For x is equal to -1, f is equal to 2. For x is equal to 1, f is equal to -2. Noticing a pattern here. And then at x is equal to 2, f is equal to +2. So what we did was we took our 4 points, our 2 critical points, our 2 endpoints, we evaluated f at all those points, and so we have -2 and 2 as our outputs. Okay, so we took our 4 points, we evaluated our function at those 4 points, and we got the outputs. We know our absolute maximum and our absolute minimums lie in there. So to find the absolute maximum, look at this right column, pick the biggest number. Between -2 and 2, which one's bigger? If you didn't say 2, then we've got a problem. Okay, now what about the minimum? Well, for the minimum, we pick the smallest number. And what's the smaller number between -2 and 2? Well, that's equal to -2. And here, I'd like to point out something again. Notice when we wrote down the absolute maximum and the absolute minimum, we wrote down the outputs. The absolute maximum is 2. The absolute maximum is not -1. -1 is a location. Where did it occur? At x is equal to -1. What is the absolute max? 2. That is what the function actually is at that point. These x values are just locations. That's not the actual maximum. So if you were asked, what is the tallest point on Earth? How high does it go? Well, you would say some giant number. How tall is Mount Everest? I don't know. 10,000 feet? I don't really know. That sounds really dumb when I say it out loud. I really should have looked that up before I started this. But where the absolute maximum occurred is at Mount Everest. See the difference? The absolute maximum is the height of Mount Everest, or how high above sea level it is. Where the absolute maximum occurred is at Mount Everest. These x values are location. F is what the actual value is. The maximum and minimum are values. They're not points. They're not locations. They're values. So the absolute maximum is 2, and the absolute minimum is -2. And instead of having to check every single number on the interval -2 to 2, we took the derivative, we set it equal to 0, we found those values, plugged those values into the function, plugged the endpoints in, and then took the biggest and smallest values of that list. That's literally all there is when finding the absolute maximum and minimums of continuous functions on intervals. That's it. If you have a continuous function that you can easily take the derivative of, and by easy, I mean that relatively, then this is the way to go. It's the true fire way to get your absolute maximums and your absolute minimums. Alrighty, now let's look at another example. Consider this situation. We have a function f of x is equal to x minus 2 sine of x, and we want to find the absolute maximum and the absolute minimum on the interval 0 to 2 pi. Well, 0 to 2 pi is a closed interval. It's good to go. X minus 2 sine of x, that's a continuous function. So extreme value theorem is going to come around the corner. So to find the absolute maximum and the absolute minimum, the extreme value theorem tells us we only have to check the endpoints and at the critical points. Now, critical points, that's where you have a horizontal tangent line or a derivative equal to 0, or a non-existent tangent line, which means the derivative does not exist at that point. So we take a look at this. We have our function is equal to x minus 2 sine of x. Now let's take the derivative of that. Well, the derivative x minus 2 sine of x is 1 minus 2 cosine of x. Now, we can look at this derivative and we can see this is going to exist everywhere. 1 minus 2 cosine of x is a continuous function, so it is definitely going to exist everywhere. And since it's going to exist everywhere, we do not have to worry about those critical points. We do not have to worry about the critical points that make this derivative not exist. We only have to determine where on this interval is this derivative equal to 0. How do we figure out where this derivative is equal to 0? Set it equal to 0. So we put 1 minus 2 cosine x equal to 0. And then we move the 2 cosine x over, divide both sides by 2. And so we get cosine of x is equal to 1/2. So the critical points occur at the points on this interval that make cosine of x equal to 1/2. This is where knowing your unit circle is vital. If you do not know your unit circle, you are not going to figure these values out. Simple as that. So x is equal to pi over 3 and 5 pi over 3. These are the two values that when you evaluate them at cosine, you get 1/2. And these are the two values that do this job on the interval 0 to 2 pi. So these are our critical values. And the extreme value theorem tells us to find the absolute maximum, the absolute minimum, or the extreme values. All we have to do is check at x is equal to pi over 3 or 5 pi over 3 and at the endpoints. How do we check them? Build a table. So remember, there is no real order to doing these things. I'm just going to go in increasing order because, well, that's just who I am. So let's start with x is equal to 0. When you plug in f of x is equal to 0. Now here's another thing I'd like to point out. Notice every time we plug it back into the original function, we do not plug it into the derivative. We do not care what the derivative value there is anymore. Because if you plug the critical points back in to the derivative, then the derivative is equal to be 0, or it's not going to exist by default. We do not care what the derivative value is there anymore. So when you're checking the absolute maximum and the absolute minimum, make sure you plug it in back into the original function. When you're doing the homework and doing these examples or something, I promise you, at least once you're going to make that mistake. If you're not careful, you are going to plug it into the derivative because the derivative is the function you were working with. That's the one that was in your hand, the one you were playing with a lot. So you're going to naturally plug it in there. Be very careful. Plug this value only into the original function f. So when we plug in x is equal to 0, we get the function value is equal to 0. When we plug in x is equal to pi over 3, well, we get the function value is equal to negative 0.6849. Don't worry, you will not be asked to do a question like this unless you have a calculator. I promise you, I'm not going to ask you to evaluate this. Just not. All right, that's for pi over 3. Now what at 5 pi over 3? When we evaluate the function at 5 pi over 3, not the derivative, we get the function is equal to 6.968. And then we have to check that last endpoint, 2 pi. We plug in 2 pi into our original function value. That's equal to 2 pi, which is roughly 6.2831. Once again, not going to ask you to calculate the 6.2831. I might have you give me 2 pi, but I'm not going to ask you to give me 6.28. That's ridiculous. The homework might. I won't. So we took our 2 endpoints, our 2 critical values. We plugged them back into our original function. And from here, we can determine what the absolute maximum and the absolute minimum are. The absolute maximum is 6.968, and the absolute minimum is negative 0.6849. Notice the absolute maximum and the absolute minimum are not at the points where it occurs. So the absolute minimum is not pi over 3, and the absolute maximum is not 6.968, or it's not 5 pi over 3. The absolute maximum is 6.968, and the absolute minimum is 0.6849. It's the actual function values, not where they occur. Be very careful about that. Because you could do all of this work, figure out this is the maximum, but then plug in 5 pi over 3. That's where it occurs. That's not the actual absolute maximum. So be vigilant when you're doing these kind of problems, because there's a couple subtle ways to mess these problems up. And they're so subtle, it's kind of hard to figure out that's the mistake you made. It's easy to check arithmetic mistakes. Checking which function you plugged it into and was it the right one, or are you plugging in the functional value or the input? That's where things get a little dicey. So be very careful when you're doing these problems. All right, so let's look at one last example on these absolute maximums and the absolute minimums. Let y equal to 6x to the 2/3 times 5 minus 2x. And we want to find the absolute maximum and the absolute minimum on negative 2 to 2. So from here, we have quite a bit of legwork to do. We have to calculate the derivative, we have to figure out where it's equal to 0, and we have to figure out where it does not exist. So let's get to it. First thing we need to do is calculate the derivative. So we have 6x to the 2/3 times 5 minus 2x. That's the product of two functions of x with each other. And when you're trying to take the derivative of the product of two functions, we have to use the product rule. It's almost like it was named that for a reason. So take the derivative of the first times the second plus the first times the derivative of the second, where in this case the derivative of 6x to the 2/3 is 4x to the negative 1/3. Don't believe me? Double check it yourself. Simple application of the power rule. Leave 5 minus 2x alone, and then plus leave 6x 2/3 alone, and then take the derivative of 5 minus 2x, which is just negative 2. Now that wasn't too bad. This is where things are going to get tricky. In this form is not really helpful to us, because in a second we're going to have to figure out where it's equal to 0 or where it doesn't exist. This form is not very useful to us for that. So we need to simplify this. So first thing I'm going to do, rewrite the fractional exponents as actual fractions and combine some things. So rewrite this x to the negative 1/3 as x to the cube root in the denominator. Multiply them together. We get 4 times 5 minus 2x divided by the cube root of x minus 12x to the 2/3. Just multiply this by negative 2. But now I want to combine these fractions. How do I do that? We have to get a common denominator. So this becomes 4 times 5 minus 2x minus 12x divided by the cube root of x. Just multiply this by the cube root of x over the cube root of x. It's just the standard technique you learned in Algebra 1 back in high school about finding common denominators. And then we can combine the fractions. And now kind of want to multiply this out and combine some terms if we can. And we get this simplifies down to 20 minus 20x divided by the cube root of x. Now this isn't a function that is a lot easier to work with, because when we have to ask ourselves these questions, where is the derivative equal to 0 and where does the derivative not exist? This form is much easier than this one. All right. Now I didn't show the calculations for finding these because it's pretty straightforward. For a fraction to be equal to 0, the numerator has to equal to 0, and this numerator is only equal to 0 when x is equal to 1. And then this fraction does not exist only where the denominator is equal to 0, or where the cube root of x is equal to 0. That only occurs at x is equal to 0. So this derivative is equal to 0 when x is equal to 1, and this derivative does not exist when x is equal to 0. So those are our critical points. Now, if you're just sitting there going, how on earth did he get that? Shoot me an email, say, hey, on this slide on section 4.1, I have no clue how you got the critical points from that derivative. Just shoot me that email, and then I'll write up a more detailed explanation for you if you so choose. All right. Otherwise, these are our critical points. X is equal to 0 and 1. And the extreme value theorem tells us that to find the absolute maximum and find the absolute minimum, what we need to do is check the critical points, and then we need to check the critical points, and we need to check the endpoints. So let's do that. Build our table. We plug in negative 2, we get 85.7196. Plug in 0, and we get 0. Plug in 1, and we get 18. Plug in 2, and we get 9.5244. Now notice something. 0 is a critical point because it forced the derivative to not exist. But just because the derivative does not exist there does not mean the function doesn't exist there. Remember, and this was a question on your exam, for the derivative to exist, the function must be continuous. But just because the function is continuous does not mean the derivative exists. So we already checked that this function is continuous. This function is continuous on this interval. That's not a problem for us. However, just because the function exists there does not mean the derivative exists there. Now, with that little spill over, we have our little tableau of values. Now we can extract the absolute maximum, which is 85.7196, the absolute minimum, which is 0. Okay, so that's all I have for you on section 4.1. Tune in with us next time where we go over section 4.2, the mean value theorem. And I will see you there where we will have more fun.